All right, welcome to another exciting episode here at Spain Park AP Chemistry. Today is Thursday, September 28th. All right, if you are enjoying these videos, please feel free to subscribe to this channel and hit that like button. And ring the bell for notifications, whatever that means. Does that mean my phone's going to be dinging this every time somebody watches it? Oh, yeah, okay, great. So you guys, when you're watching it at 2 o'clock in the morning tonight, on my phone, actually I have it on silent, so it won't.
Wait, no. It means like when you post, they get notifications.
Oh.
Like when you post
When I post a new one, then you get notified. Yeah, ring that bell. All right, we're looking at this, and this part is super obvious: solid, liquid, and gas. But if something, and you don't have to follow me, just kind of keep it on there. If something is a solid at room temperature versus a liquid versus a gas, what does that mean about the attractive forces in the solid? They're the strongest of the three. Okay, so we can use that, the melting point, boiling point. If it's a solid at room temperature versus something that's a liquid, the liquid has a lower melting point. It melted at a lower temperature than the solid did. That means the liquid had weaker attractive forces. There was enough energy at room temperature to begin breaking and stretching those bonds. So we use that as our guide, as our evidence of attractive forces. So we can just kind of look at those. We already kind of looked at that first part. Now, we're going to eliminate question number 11. We don't need to, we'll never have to know the answer to that one, because there's conflicting issues going on there, so don't worry about number 11. But if I look at number 8, assign each molecule in table 2 as either polar or nonpolar. How do I do that?
Well, we know all hydrocarbons are going to be nonpolar, so.
Okay. So when I look at this table right here, I skipped to page 3, but when I look at this table, how do I know which ones are polar, which ones aren't?
phone call.
First off, Luke, what was the first thing you said?
You know all hydrocarbons are going to be nonpolar.
Okay, and I don't think I said that yesterday. You know all hydrocarbons, if it's just carbon and hydrogen, you can assume it's nonpolar. All hydrocarbons are nonpolar. Once we get to chapter 6 through 9, and we learn about, we relearn, we refresh, we review about structure and shape and polarity, we'll get into more about how the shape of the molecule affects the polarity as well. But for right now, we can just know that these two are going to be nonpolar. Strictly because they're hydrocarbons. If it's just carbon and hydrogen, you automatically know it's nonpolar. So what's the only type of attractive force between nonpolar molecules? LDS, right? So, how does the strength of the LDS vary within a molecule, from molecule to molecule? If it's bigger, then it's got stronger LDS. And technically, what's bigger? The electron cloud. And you need to just say the electron cloud is bigger. And that's just one of the nitpicky things about AP on this one. You just say it's got a bigger electron cloud, so it's going to have stronger LDS. So notice the boiling point from CH4 to C2H6, the molecule got bigger. So the boiling point, now it's negative numbers, so the boiling point went from negative 161 to negative 88. It got to a higher boiling point. Now it's still relatively low because these London forces, not relatively, it is very low, because the London forces are weak. So these two are very much a gas at room temperature. You have to cool them down significantly before the molecules are going slow enough to where those attractive forces can actually start sticking together. All right? Now, what about HCl? How do I know what HCl is?
Phone call.
Phone call. What does phone call mean? If a fluorine, oxygen, nitrogen, or chlorine are present, it's probably going to be a polar bond, unless they're bonded to themselves. Okay, so if it's F2 or Cl2 or N2O2, those obviously the difference in electronegativity is 0. But if it's bonded to anything else, it's going to be significantly more electronegative than the other thing, so it'll probably be a polar bond. So I know that this is polar. So what type of attractive forces does it have? Dipole, and everything always has LDS. You always have LDS. It's always an answer. LDS maybe plus. If it's polar, it's got LDS plus dipole.
So they build off of each other?
No, it's just everything's got London dispersion forces. But only polar molecules have dipole. And then what about these two? What's unique about them?
Hydrogen bonds.
They have hydrogen bonds. And how do we know that?
FON.
FON, fluorine, oxygen, nitrogen. But not only that, you got to have a hydrogen attached directly to them. So you have HF, and so these have hydrogen bonds. And if it has hydrogen bonds, it has all three. So it also has dipole, and LDS. So notice it's got the strongest of your intermolecular forces. But the melting point of HF is 20, H2O is 100. So what does that mean about water's attractive forces versus HF?
Much stronger.
Much stronger. Because water has two places for it to hydrogen bond with another water. It can hydrogen bond there, and it can hydrogen bond here, and it can even hydrogen bond here, like this, there. So there's so they kind of attract every which way. So water's got relatively strong, for as small a molecule as it is, it's got relatively strong attractive forces. So its boiling point for a small molecule is pretty high. And it's got a high specific heat, so it takes a lot of energy to get it moving and all those different things. So water, because of these hydrogen bonds. So when we're talking about boiling points, always be aware of hydrogen bonds. When in doubt, the answer is hydrogen bonds. Which is the highest boiling point? If they give you a list, look for hydrogen bonds. Okay? Now, notice all of these, though, are relatively low. If I try and melt sand, or salt, something that's an ionic bond, sand's not ionic, salt is an ionic bond. What did it say about the energy needed to melt those? Does salt melt at 100 degrees?
No.
No, it's like 800 degrees. It's pretty high. It's super high. Okay, so ionic compounds are going to have a much higher. So what do we use to measure the strength of an ionic bond? Lattice energy, which is measured by Coulomb's law.
Since you mentioned sand, which would be like stronger, like a regular covalent bond or a covalent molecular bond?
Okay, the covalent bond in sand and in any other covalent substance, the covalent bond itself is going to be strong. It's just in a covalent network, there's all covalent bonds, so you have to break that covalent bond. But in water, you're breaking just the IMFs, so they're going to be much weaker. Now, the bond here between the hydrogen and the oxygen is nearly as strong as the carbon-to-carbon bond here. It's just we don't have any weak bonds in this, whereas we have the weak bonds, the IMFs, in the water. Okay, so the covalent bond, the intra-bond, is the same. It's just the fact that it doesn't form a molecule, so there's no weak bonds holding molecule to molecule. Does that make sense? All right, good question though. All right, so we needed this is a good thing that we have to look at, and we're gonna, as we go through the year, we'll do this more and more and more. But hydrocarbons are always nonpolar. Phone call, phone for hydrogen bonds. All right, so that's the first part of this. So if I go now to this page here, what do we find then? The more polar the molecule, the higher. The more polar the molecule, what does that mean then about its intermolecular forces? Stronger. Okay? Now, this is the one here that we have I think this is the one that's the wrong information, yes. Did I give you the right information? Did I do a correction on this? Yeah? Okay. So what were the correction on here, that's crooked. This is supposed to be, what did I say, negative 101.5, I think it said negative 102. So it all depends upon which one you have, negative 102, negative 101.5, doesn't matter. About the same.
This one has boiling and melting points. So the boiling points are there, and then it adds a column of melting points on the right.
Huh.
Wait, how does yours not? Yeah, that's on my side.
Oh, is it this one? No.
No, no,
Your table is just missing the.
Really? Huh. How do I have different forms of that one? All I have is one with the answers on it.
I mean, you can show that one.
Shit. That's crazy.
no, it's the melting points that are wrong.
Okay. So I think, is this the one?
Yes.
Am I right now? Okay, so this one
It's,
is negative 102.
Yeah.
Yes.
This one is
Negative 7.
negative 7 point,
Just that.
just 7. And this one is
114.
114 degrees. Okay, what happened is, what I figured out when I saw, everything I have, I pretty much, if it looks like this, I steal from the internet. And so, if it's not there, I figure it's free.
That's what I figured about.
So, I'm not selling it. So anyway, we have this, these are the Kelvin temperatures, not the Celsius temperatures. And so they kind of mixed and matched the Celsius and Kelvin, which has kind of made it go crazy. So if I'm looking at these attractions, now, F2, CL2, BR2, I2, what does that mean about the polarity of each of these things? How do we know that's nonpolar?
Two bonded together.
Equal. The electron negativities are going to be equal, so it's going to be a perfect sharing of electrons. These are the ones that are perfectly nonpolar. So if it's a diatomic molecule, we know they're all nonpolar. So the first thing that's important when we're talking about boiling points, melting points, what type of substance is it? Is it ionic? Because if it's ionic, we go to lattice energy, Coulomb's law. If it's covalent, we need to know, okay, it's IMFs, so what type of IMFs? Is it polar or nonpolar? If it's polar, do we have hydrogen bonds? We just kind of go to the progression because we need to know the strength. So these are all nonpolar. So what is that? What's the only type of attractive force? Only LDFs. So with what do LDFs vary? Size of the electron cloud, right? So we're going down fluorine, chlorine, bromine, iodine down the periodic table. So what's happening to the size of my electron cloud? It's getting bigger, so what's happening to my attractive forces? Getting stronger, so what is happening to my boiling point and melting points?
Higher.
Getting higher. Okay? So it says which one's a gas, which one's a liquid. Well, the melting point determines whether it's a solid, liquid, or gas. So if it melts at negative 220, well, at room temperature, we're above negative 220. At room temperature, we're above negative 188. So what state's this going to be at room temperature?
Gas.
A gas. Okay? Chlorine boils at negative 34. Well, that's still below room temperature, right? Room temperature is generally 25 degrees Celsius, if you didn't know that. Okay? So if you want to write off to the side, room temperature equals 25. It's really about 22, and here it might be 20. And so, but negative 34, that's still going to be a gas. But if it's 59, this 59's above the 25, right? But the negative 7 is still below. Okay, so it's going to melt Okay, that 25 is above the -7, so it'll melt at room temperature. But, so what state's it's gonna be?
Liquid.
It's gonna be a liquid. But this one here, iodine, it doesn't melt until 114 degrees. So what state's it gonna be?
Solid.
Solid. Okay? And that's why, again, on the periodic table, red means gas, blue means liquid, black means solid. On your color periodic table that you have,
Oh, wait, that's.
the color of the element tells you the state. Outline means it's man-made, doesn't exist in nature.
What does black mean, you said?
Solid. So there's only two liquids,
Mercury.
mercury and bromine. Okay, mercury and bromine. And bromine's going to be a very volatile liquid. It's going to evaporate relatively quickly because it only has these weak London forces holding it together.
Why is tech?
All right, given that, okay, we already answered, they're all nonpolar. Is there a relationship between boiling point, polarity and boiling point?
Yeah.
On this one,
No.
because they're all nonpolar, so there's no relationship there. What is the relationship between the molecular weight and the boiling point?
The higher the weight.
The higher the weight, but I don't like the wording on this because we can't say it's got stronger forces because it's got bigger molecular weight. What do we say?
It is a larger electron.
Larger electron clouds. So really change the molecular weight to larger electron clouds, larger size of the electron cloud, because it's more polarizable. Okay, and again, I don't know how to get the, hopefully you have the vision just of a big, like amoeba, a big, flexible mush that can, the more it can distort, the more you can push it over, the more electrons that are on this side, the less electrons that are over here, and so this is more negative, this is positive. If we have just a tiny electron cloud, it only distorts a little bit. We only have a few electrons distorted. So the positive negative isn't as much. So the bigger the electron cloud, the more distinct, the stronger the London dispersion forces can be. Okay? That's how it works. And so when they bump into one another, they distort. So the bigger they are, the more they can distort, the more they can smush. The fancy word, the more polarizable they are. They can become more polar. All right. Let's keep going because this stuff's good stuff. I've lost where I was. All right. Let's go. Was that the end of page 3?
There's one more question.
One more question on page 3. If I put my glasses on, I might be able to read it. Page 2, page 1. What happens to page 3? Page 3. As the molar mass of a compound increases, the strength of its intermolecular forces increases. But what are we going to change the molar mass to?
Electron cloud.
The size of the electron cloud. Okay? So what's the relation between molecular weight and boiling? The greater the molecular weight, really the larger the electron cloud, the greater the boiling point. And again, as the size of the electron cloud increases, the strength of the intermolecular forces increase. Okay? Believe it or not, if this person who wrote this worksheet answered the question in terms of molar mass like this, they would not get credit on the AP test. Okay? That's why I keep stressing this. You have to say the size of the electron cloud. All right. Page 4. There's page 3. What happened to my page 4? I just said. I cannot keep track of anything right now. Here's page 4. All right. So again, does the statement we just said previously agree with this? Well, helium, neon, argon, krypton. Those are noble gases. What's unique about a noble gas?
They don't want to bond.
Well, they have a field octet, which means what? I heard somebody say.
They don't want to bond.
They're stable, so they don't bond with anything. That's what you said in the back. I was trying to get you to say it again. Okay? They don't bond with anything, including themselves. So their entire existence as single monatomic atoms. But they're considered a monatomic molecule. So in other words, the only thing holding or attracting helium to helium is going to be weak London forces. Neon to neon is weak London forces. Even helium to neon would be weak London forces. That's why they're all gases at room temperature, because they only have those small electron clouds. They don't have a big molecule. Even though it's 86, it's still just one atom with that one electron cloud. So it doesn't distort readily. So they have weak London forces. So you can see that their boiling points are very low. Very low. But what's the trend? As you go down in the family, this gets higher, relatively speaking. Notice here, CH4, C2H6, C3H8, C4H10, as the molecule's getting bigger, as the electron cloud's getting bigger, what's happening to my boiling point? But notice again, they're all still low. They're all still going to be gases at room temperature, because the only attractive force is LDS, which are all weak. Okay? I'm just trying to help you kind of see, and a figure repetition is going to help.
Mr. Hobbs, do you ever wonder what solid helium looks like?
Have you ever heard of the LHC, the Large Hadron Collider? Okay? It is in CERN, Switzerland. It's a 23-kilometer underground particle accelerator.
Don't they like smash things?
And they smash things together, and they're trying to find new subatomic particles. One of the subatomic particles they're trying to find, that they say they found, is called the Higgs boson. Now, classical physics needs the Higgs boson to exist, because the Higgs boson supposedly generates this field that, as energy goes through it and is converted into mass, the slower it goes through it, the more mass that gets assigned to the mass that's created. So if it goes through quickly, then it only gets a little bit of mass. If it goes through slowly, it gets more mass through this Higgs boson field. Okay? And they had never been able to find it before, but apparently in this thing, I've read conflicting things, that they for sure have found it. Others say that there's like down to a 1 in 1,000 chance, versus a 1 in a trillion chance that it exists. I don't know. Okay? A lot of people refer to the Higgs boson as the God particle, because that's what supposedly gives the mass to particles and distributes it out. But anyway, at this LHC, where they're doing all of this, in order to accelerate the particles that fast, they have to cool it down to near absolute zero. They use liquid helium to do that. And so it takes them like 2 months to cool the helium down, to liquefy it, and then to fill this chamber full of the liquid helium to get it cooled. And then when they shut it down, then they have to pull it all back out and do the process all over again. So it's a major ordeal. So liquid helium, I've never seen solid helium, but I know that they use liquid helium. And let me see, when you go to over here, 4 degrees Kelvin is liquid. In order to get helium to be a solid, you got to go to 0.95 Kelvin. That's near absolute zero. 0.95. Now, supposedly solid hydrogen has, when it's a solid, it becomes a superconductor and actually has some metallic characteristics. I've never seen a picture of it, but apparently solid oxygen has a pale blue color to it. Solid oxygen does. Anyway, just interesting. Yeah.
If you drank liquid helium, would it produce the same effect?
No, it'd kill you.
Yeah, but
You'd be the freeze.
no, if you were like Superman and like
No, because then it's a solid. It's gonna be more dense, or liquid. It's more dense.
So what happens if you walk in that room and the liquid side? It's like instantly die.
I mean, first off, it's a channel. It's not a room, but
What if you like stuck your finger?
oh, it'd freeze instantly.
Yeah, but it's
You lose it. Instant frostbite.
It's like you live the opposite.
You can try to tap it, it'd probably fall off or something.
Yeah.
Okay, so according to graph 1 at the right. Now this is right off an AP test. According to the graph at the right, notice our trend here, CH4, SiH4, GeH4, SnH4. Notice on the periodic table again, you're just going right down, you don't have to go to the periodic table, but you're going right down the carbon family, silicon, germanium, tin, okay? So carbon, silicon, germanium, and tin. They're all going to be symmetrical molecules, and so they're all nonpolar. These are all nonpolar molecules. So what's happening to the melting point and why? As you go down in the family, it's increasing because
There's a larger electron.
larger electron cloud, stronger LDS. Now the same basic trend, you're going down the oxygen family. H2O, H2S, H2SE, H2TE. There's no foam call here, so these are predominantly what type of molecules? Nonpolar. Why is water, why doesn't it follow the same trend?
Hydrogen bonds.
Because it's polar and it has hydrogen bonds. So the exception, this is an exception because these only have, if they do have dipole-dipole, they're only going to be very weak dipole-dipole. And London dispersion, whereas water has the much stronger hydrogen bond, so it's going to be that anomaly, it's going to be that exception to the trend because it has those much stronger IMFs. This is what you look for. This is the type of question that they're going to say, why is this one unique? What's going on here? In which substance are there stronger intermolecular forces, SnH4 or CH4? Well, and how do you know?
Because
That's higher.
Higher boiling point. Okay? And then we can explain the higher boiling point because it's going to have a bigger electron cloud, stronger LDS. But that question just says why, because the higher boiling point, that's what determines it. Okay? Now, explain based on what you have learned so far, your choice should have stronger molecular forces. We just did that. Okay? Which is stronger, H2S or H2O? H2O. So, explain why. Mostly due to polarity or molar mass?
polarity.
Polarity, but more specifically, even than polarity,
Hydrogen bonds.
the hydrogen bonds. Right? Now, continuing on in the same line, this too is on an AP test at one point. Now, your graph is easier to see, but I have to keep it small so I can get all the questions on there, but you're looking at it on your paper. I don't like it when it's crooked. Close enough. So now look at the trend. Here's my CH4, that trend, but then we go to the NH3, so the nitrogen family, just doing it with the hydrogens. And then we're doing HF, going down the halogens, HF, HCl up, and then we're doing it with the oxygen family. What is unique about these three that's going to cause them to be anomalies in the trend?
Hydrogen bonds.
All three have hydrogen bonds between the molecules. You always have to say between the molecules. It's not the H to F bond, it's the HF bonded to HF bond, is the hydrogen bond. It's the between molecules.
Isn't dipole-dipole only like for the car?
Yes. Okay, so these actually still, HCl is going to have some dipole-dipole, but then H2S is just getting bigger, and then H2TE is even bigger, so the London forces are getting stronger.
How come H2O has such a high boiling point compared to HF when HF should have a larger,
Because of all the different places that can form those hydrogen bonds that we talked about at the
okay.
beginning of the year, at the beginning of the period. Okay? And again, you really won't ever have to explain that, but what we could explain is we know that water is going to have the highest, the strongest attractive forces because it has the highest boiling point. But the AP is going to ask more about the anomalies. Why we have the difference in the trends? Because these three have hydrogen bonds, these don't. Can you recognize which ones have hydrogen bonds, which ones don't? phone, F-O-N, and that's an example of all three. Okay? So, which three compounds deviate from the linear relationship that seems to be present between the boiling point and row number?
H2O, HF, and
H2O, HF, and H3. That indicates the three compounds listed in part A have what?
Stronger.
Stronger intermolecular forces. Besides hydrogen, what other elements are there?
Oxygen, fluorine, nitrogen.
Okay, and really that's kind of a redundant question. So complete compounds containing hydrogen bonded to the elements form very strong bonds. What elements we put in there?
Fluorine, oxygen.
Phone, F-O-N. All right. Are hydrogen bonds the same as covalent bonds?
No,
Oh.
Okay, why not?
because they're covalent bonds are in between each element.
Okay, so,
Because they're intermolecular.
okay, say that, you guys are both saying the same thing.
Because they're intermolecular.
So hydrogen bonds are intermolecular, whereas Tracy, what did you say? The covalent bonds are intramolecular, within. Okay, so which one's stronger? Covalent bonds, a little bit or a lot?
A lot.
A lot. So which bonds, when you heat something up, which bonds break first?
Intermolecular.
The intermolecular, the hydrogen bonds, or the dipole-dipole, or the LDS. Okay, so when CH4 is a liquid that's super, super cold, you begin warming it up, the carbon doesn't break apart from the hydrogen, CH4 breaks apart from CH4. You break the weak London force, you don't break the strong covalent bond. And then lastly, what is the main difference between, I really just said that, a hydrogen bond is intermolecular, whereas a covalent bond is intra, between versus within. Are y'all, I mean, I know we did it in chemistry 1, but it was a long time ago. I don't know to what degree Mr. Graver went into this. Okay, I know I went into it pretty extensively. I think we actually did this worksheet in my class. Okay, but this is going to carry through all year long on different things that we talk about. So it's very important. That's why I'm taking the time, making sure that we understand all of these different things. Does anybody have any questions about how you know this or how you know that? And again, as far as how to tell whether a molecule is polar or not, we're going to get into much deeper detail at the end of this first semester. Okay? All right. So let's finish the notes, and then we'll look at some practice. What do I have? 10 minutes?
Yeah, you got.
Time keeps on slipping.
Oh, no, can you sing a song for us as we, as an intermission?
Yeah. Here's an old AP question. Here's a multiple choice, two multiple choice questions, 3 and 4. Take a second. You don't have to write them down anywhere, but just take a second and answer these. Number 3 and number 4. Pick an answer for both of them. Okay, with 1 being an A, 2 being a B, 3 being a C, 4 being a D. On number 3, what are we thinking? Just kind of don't hold it way up, but just kind of flash me. What do we think the answer is to the number 3? Okay. All right. Okay, so I'm seeing different answers between 1 and 3. 3 was C, bromine to bromine bond. When bromine goes and becomes gas, are we breaking the bromine to bromine bond?
No.
What are we breaking?
The intermolecular.
The bond between the molecules. Now, I would rather this word, rather than saying forces among bromine molecules, I would rather say forces between bromine molecules. Okay? But this one is talking about here. But if it's a liquid and this is a gas, which one's got stronger intermolecular forces? The liquid. Okay? So this is what the misconception they're always trying to overcome is that when a substance goes from a liquid to a gas, are you breaking the intermolecular forces or are you breaking the covalent bonds? And we're breaking the intermolecular forces. This is talking about the covalent bonds. These are going to be much stronger. None of this tells me anything about the strength of the bromine to bromine or chlorine to chlorine bond. Okay? It only tells me the strength between the intermolecular forces. It tells me that bromine is going to have stronger than chlorine because it's a liquid at room temperature. Now, what does it mean with a high vapor pressure, though? It's not really relevant to the answer, but what does that mean if it has a high vapor
Takes
pressure?
a lot of energy to turn into a gas. Or no?
It's the opposite.
Yeah.
Okay, high vapor pressure. Vapor is the gas above the liquid. Okay, hey, listen. Vapor is the gas above the liquid. So if it's got a high vapor pressure, that means there's a lot of gas above the liquid, a lot of vapor above the liquid, which means it's evaporating quickly, meaning that it's got weaker. So bromine, it is a liquid, but a high vapor pressure, meaning it's evaporating quickly because it still only has the weak London forces holding it together. So it's, even though it's a liquid at room temperature, it's still going to tend to evaporate quickly because it only has weak LDFs. Okay, so I got to get an answer for number 4 here. Decreasing polarity. So which one do you want first? The most polar, right? Good. Hey, how did we know? Okay, we use periodic trends. So we know fluorine is the most electronegative. You know this is going to be 0. So this is always going to be last. Okay? But this is the strongest, whereas O and N, they're right next to, that's 2 big boys right next to one another. Okay, so there's going to be a little difference between them. Okay? So, but as far as decreasing order, I'm trying to figure out how we hear. So this is reversed. Okay? SBI, SBTE, SBCL. Okay, again, SBTE, SBI. Oh, see, the I and the TE is where you're going to have the trend. So it's really asking about periodic trends. But this one's just the most obvious. Okay? I mean, I can just see that one right, just like that. Okay. Notes. I want to get finished so we can. Factors affecting the maximum solubility. In other words, how much dissolves. This is pretty straightforward. Okay? We have our solute plus solvent goes to solution. But if it's positive, if it's endothermic, heat's going to be on the left. You're adding heat to make it dissolve. If it's exothermic, heat's being released when it dissolves. Did I do this? Didn't I do the sulfuric acid in water? Do what y'all add the acid to the water and it got super hot?
Yeah.
That's an extremely exothermic heated solution right here. All that heat, when the sulfuric acid mixed with the water, it got super hot. Okay? So it all depends upon these two. Now, Le Chatelier's principle simply says when a system is at equilibrium, and that means it's a reversible reaction, if you add a stress to it, the reaction is going to shift in such a way as to relieve the stress. In other words, it's always going to go away from whatever you add. So if it's endothermic and I add heat, it's going to want to go this way and make more dissolve. If it's exothermic and I add heat, it's going to want to go this way and make the two separate. Okay? That's our teeter-totter, yeah. Okay? So we're balanced. And I add something to this side. What does the reaction have to do to get back to balance? It's got to go that way. If I add something on this side, to get back to balance, it's got to go this way. It's always got to go away from what you add. That's all the Chatelier's principle says. So the heat of solution tells me if it's positive or negative. Now, what do we know with solids? How do you get more? Do you do your dishes in cold water or hot water?
Hot.
Why?
You don't get the grease.
More things dissolve in hot water than they do in cold water. So what does that mean? Most things have a positive or a negative heat of solution. If I add heat, make it hot water versus cold, hot water is going to make it go to where more dissolves and the dirt comes off. Goes down the drain. Okay? Most solids and liquids have a positive heat of solution. In other words, you increase the temperature, you increase how much can dissolve. We saw that with our potassium trisoxylatoferic 3-trihydrate. We did it in hot temperature, it dissolved, and then we put it in the ice bath, took the heat away. This time, we took the heat away, and we made it come back this way, and the solute separated from the solvent. The green crystals precipitated out from the water. They separate. Plus means two separate terms, right? Whereas here, they're together. That's dissolved. So that's the most common thing, is that if we have a positive heat of solution. Now gases, all gases have a negative heat of solution. So if you increase the temperature, so if you put your soda out in the sun, it goes flat because all the CO2 comes out of solution. And we'll pick up there tomorrow.